Hi, this presentation deals with an investigation of challenges specific to open-loop predictor model-based parameter identification of electric drives. Let me first briefly introduce myself. I'm Aravinda Pereira, a PhD research fellow in the Norwegian University of Science and Technology, Trondheim, Norway. My PhD research is about adaptive and sensorless control methods for three-phase and six-phase drives for seabed mineral mining. The outline of the presentation is as in this slide. Let me guide you through step by step. First, the motivation and the background. Figure 1 illustrates the overview of the IPMSM drive in which the online parameter estimator, OPE, is incorporated. The detailed OPE is given in the figure 2. Recursive prediction error method based identification of IPMSM is discussed in the given references. Under the adopted approach, the stator currents are predicted using full order model and used to generate prediction error, which is assumed to be existent only if the parameter discrepancies are present. The full order model based predictor is arranged in open loop, thus open loop. Thus, epsilon becomes well conditioned with parametric errors, which is one reason for the effectiveness of this identification technique. However, due to the absence of a feedback loop in the predictor, its eigenvalues are not adjusted in real time and their imaginary paths escalate in proportion to the rotor speed. This phenomenon demands caution during the design and digital implementation of the predictor in preventing potential instabilities, particularly in the high-speed region. Now let's dig into the details of the stability issues of the predictor. You see here the full order model in equation 7 and the system matrix in equation 8 and the respective eigenvalues in equation 9. The real part of the eigenvalues is machine impedance and nominal electrical frequency dependent. The imaginary part, on the other hand, has a speed dependent component, which is this one, that is dominant compared to the speed independent components. Therefore, the imaginary part can be approximated to this speed dependent component. It is known that the imaginary part corresponds to the natural frequency of the system. Thus, it can be expected that the oscillation frequency of the predicted currents increase in proportion to the rotor speed. The eigenvalue trajectories in continuous time domain can be plotted as in figure 3 for a 4-pole 2100 rpm IPMSM. The figure shows that the predictor is stable in the continuous time domain across the entire speed range, despite the imaginary paths are escalating with speed. Now let's investigate their stability in the discrete time domain. In order to implement the predictor in a digital controller, full order model needs to be solved for currents and discretized, for which one can use an explicit numerical method like the forward Euler method or an implicit method like the trapezoidal rule. Despite the ease of computation, the explicit methods offer a limited stability region in the left half plane, unlike the implicit methods that offer stability theoretically in the entire left half plane. The predicted currents become as in equation 10. With the Euler's method, the final expressions with the trapezoidal rule is omitted, however, can be derived using equation 11. Figure 4 illustrates the behaviors of the same eigenvalues, but now in the lambda h plane, where h stands for time step in the digital controller, when discretized using the above two numerical methods and applying typical h values corresponding to DSP-based and FPGA-based implementations. Unlike in the case of continuous time domain, this figure illustrates that when h equals 125 microseconds. A typical step time in DSP controller in IGBT drives, the eigenvalues can escape the stability region with use of Euler's method. Yet they are still within the stability region with respect to the trapezoidal rule. This potential instability with the Euler's method can still be circumvented with a choice of narrower time step like uh, h equals 1 microsecond, a time step achievable using FPGA. Let's briefly look at the implementation of the methods. In the DSP, the predictor is implemented using the C++ programming language in the fastest interrupt routine with h equals 100 h equals t sub equals 125 microseconds. In the FPGA, the predictor is programmed using a schematic language known as the Xilinx system generator. The program looks as in figure 5. The predictor still follows the same structure as in figure 2. The resource utilization from the predictor intellectual property core is given in the full manuscript. Next, we will look at the validation. The proposed implementation method of the predictor are investigated using Xilinx system on chip based embedded real-time simulator or ERTS in short. The methods are demonstrated by adapting magnet flux CM and RS state resistance online. The overview of the ERTS is illustrated in figure 6 and the associated hardware is presented in figure 7. The detailed design of the ERTS is found in the given reference. Table 1 tabulates the experimental plant data. The steady-state behavior of the different predictor implementations and the effect on the estimates will be evaluated, particularly at high rotor speeds. To keep the discussion within the scope, only magnet flux adaptation is considered, assuming the other parameters are in agreement. The predicted currents, prediction error, update terms, and the estimated magnet flux are plotted in figure 8, in which column A, B, and C are dedicated to the rotor speeds 0.4, 0.6, and 0.8 per unit respectively. The legends stand to the right of the image, in which E denotes the Euler method based in DSP. T denotes the trapezoidal method in DSP, and F denotes the Euler method in FPGA. By looking at the oscillation frequencies, it can be confirmed that the oscillation frequencies of the predictions are directly proportional to the rotor speed based on this equation. The rotor speed dependent oscillations are superimposed on epsilon, so in the update term and inevitably in magnet flux, thus in the electromagnetic torque. The Euler's method-based predict implementation in DSP displays an unstable behavior when at 0.8 per unit. This suggests that the Euler's method cannot guarantee stable estimation across the full speed range. Therefore, it is not suitable for the cause. Opposing to the DSP-based method, FPGA-based predictor results in nearly no oscillations, thus yields smooth and steady magnet flux estimation irrespective of the rotor speed. An investigation is carried out between the dynamic performance of the trapezoidal rule-based DSP predictor and the Euler-based FPGA, and the results are in figure 9. And it turns out that FPGA offers more stable and ripple-free, oscillation-free adaptations. In conclusion, when the open-loop full-load model-based predictor is concerned, oscillation frequency are seen to increase in proportion to the rotor speed. And when DSP-based implementations are concerned, in silicon IGBT drives, trapezoidal rule-based method can guarantee stability, not forward Euler method. FPGA-based predictor implementations offer better performances. Thank you for your attention. I am happy to answer your questions in the later part of this presentation. Thank you. Bye bye.